Hello everyone, myself Aruna, working as lecturer in Department of Computer Science and Engineering. I welcome all you to the session 12 in the unit 2 Logic Circuits. In this session, we'll have brief discussion on the topics called as counter and its types and asynchronous counter and the decade counter. Finally, we'll have a look on MCQs with respect to the counters. First, we'll see what is a counter. Counters are specific type of sequential circuits. These specific type of sequential circuits mainly used to count the sequence of input pulses. These input pulses we will fed or present to the counters in the digital form. Digital form means it will be in the form of zeros and ones, binary form. After counting, the output values will be incremented or increases by 1 on every clock cycle. For every clock cycle or for every clock, the output value will be incremented by 1. Then if it reaches to the last value at the last state, the output will be wrapped back or moved back to the initial stage called as the first stage called as the 0th stage. The output value will be incremented by 1 on every clock cycle. So, we will call this specific type of sequential circuit as counter because the output value will be incremented by 1. These counters are made up of or consist of the flip-flop, group of flip-flop or set of flip-flops. Now we'll see how the counters works. If the present state of the counters are 0 and 0, the next state of the counter will be 0 and 1. If we convert 0 and 1 to the decimal value, it will be 1. If the present state is 0, the next state of the counter will be 1. If the present state of the counter is 0, 1, that means decimal value 1, the next state of the counter will be 1, 0. Decimal value for 1, 0 is 2. If the present state of the counter is 1, 0, that is decimal value it is 2, then the next state of the counter will be 1 and 1. The decimal form of 1 and 1 will be 3. If the counter reaches to the last state of the maximum value, the output value will be moved back or wrapped back to the initial stage. Here the initial stage is 0, 0. The last state or the output state is 1 and 1. It counts from 0 to 3. 0, 1, 2 and 3 and it will be wrapped back to the initial stage. This can be symbolically we can represent in this fashion. Okay, if the present value is 0 and 0 for the first clock pulse or the first clock it will be incremented by 1. 0 to 1. For the next input clock pulse, it will be incremented by 1. That is 0, 1. Decimal form is 1. It will be incremented by 1. Decimal form of 2 is 1, 0. 0 afterwards it will count 1. Next one is it will be incremented by 2. Next, for the next clock pulse, input clock pulse, this 1, 0 will be incremented by 1, then we'll get the value 1 and 1. If we convert 1 and 1, we'll get the value 3. Here, let us observe the counter counts from 0, it will be incremented by 1, 1. Next, it will be incremented by 1 more 1, it is 2. It will be incremented by 1 more 1, it is called as 3. It reaches to the last state. If it reaches to the last state, it will be moved back or wrapped back to the 0th state. 0th state. So, for every clock pulse, it will be incremented, the output value will be incremented by 1. This is how the counter works. Now, we'll see what are the benefits of the counters. As we all know, the counters are used for the counting purpose mainly. The output value will be incremented by 1. So, these counters we can use it in simple clocks for tracking of the times. Next, these counters can also be used to count, such as how many bits have been sent or received. To count that also, we will use the counters. And these counters can also be used to count how many steps have been performed in any of the computation. To keep track of those counting, we can use the counters. And these counters can also be used in our computer processor. The processor consists of the special type of register called as the program counter. This program counter mainly it is used to keep track of the instruction that currently being executed. Okay, this currently being executed instruction, it has to keep track means the instruction has to be incremented by 1. For incrementing the instruction 1 by 1, we need some special type of circuits. Here we will use the special type of circuit called as the counter to increment the counter for every clock cycle to point to the next instruction that is to be executed. So these counters can also be used in the PC, that is program counter. These are the different benefits of the counters because these are used for counting purpose. Next, we'll see the types of counters. There are two types of counters. One is the asynchronous counter, another one is the synchronous counters. First, we'll see about the synchronous counters or the asynchronous counters. In this asynchronous counters, the clock pulse will be applied to the first flip-flop. We will apply clock pulse to only the first flip-flop. As I told you, these counters are made up of set of flip-flops or it consists of group of flip-flops for counting purpose. In these counters, in the asynchronous counters, we'll apply the clock pulse to the first flip-flop itself. We won't apply the clock pulse to all the flip-flops present in the counters. In the asynchronous counter, clock pulse will be applied only to the first flip-flop, Then output of the first flip-flop will act as the clock pulse input for the second flip-flop. Here we won't apply the clock pulse to the second, third and so on. Clock pulse will be applied to only the first flip-flop. Then to change the state of the second flip-flop, the output of the first flip-flop, we will give it as a clock input to the second flip-flop. Then output of the second flip-flop will act as a input for the third flip-flop and so on. Please remember here, in the asynchronous counter, clock pulse is applied only to the first flip-flop. The examples for the asynchronous counters are ripple counter and the decade counter. The next type of flip-flop is the synchronous counters is the synchronous counters. In these synchronous counters, the clock pulse will apply to all the flip-flops simultaneously. That means in parallel or at a time. For all the flip-flops, clock pulse will be entered. But in the asynchronous flip-flop, the clock pulse will be fed or given to only the first flip-flop. But in synchronous counters, clock pulse will be given to all the flip-flops at a time or in parallel or simultaneously. Example for the synchronous counters are ring counter, Johnson counter and the up-down counter. These are the two types of counters. One is the synchronous counter, another one is the asynchronous counter. Now we'll see the difference between the synchronous counter and the asynchronous counter. Let us compare these two counters, synchronous and the asynchronous counter. Synchronous counter. As we all know, these synchronous counters, flip-flops will change their states simultaneously. All the flip-flops states will be changed simultaneously or in the parallel because the clock pulse is connected directly to all the flip-flops. So, the state of the flip-flop will be changed simultaneously. All flip-flop states will be changed simultaneously because clock pulse is connected directly to all the flip-flops. But in asynchronous counters, all the flip-flops do not change their state simultaneously because the clock pulse is not connected directly to all the flip-flops, but the clock pulse is given to only the first flip-flop. So, in the asynchronous counters, all the flip-flops do not change their state simultaneously, but in the synchronous counters, all flip-flops change their state simultaneously because clock pulse will be connected directly to all the flip-flops. This is the main difference between the synchronous counters and the asynchronous counters. Then, with respect to the synchronous counters, these synchronous counters requires maximum hardware, but asynchronous counters requires minimum hardware. Next difference is synchronous counters works with high speed. That means operation speed of the synchronous counter is more because clock pulse will be given to all the flip-flops simultaneously or at a time or in parallel. If we give clock pulse at a time, the operation speed will be more. Next, with respect to the asynchronous counters, operation speed is slow because here clock pulse we won't give at a time to all the flip-flops, but clock pulse will be given only to the first flip-flop. So, operation speed is slow in case of asynchronous counter and operation speed is more in case of synchronous counters. Next, the synchronous counters will not suffer from glitches or spikes. Glitches or spikes mean sudden malfunctioning, sudden repair. The synchronous counters won't suffer from sudden malfunctioning, but the asynchronous counters will suffer from sudden glitches, that is sudden malfunctioning or sudden spikes. Next, synchronous counters, we will call it as the parallel counter. It can also be called as parallel counter because clock pulse is connected to all the flip-flops directly or simultaneously. We will enter the clock pulse to all the flip-flops. So, we will call it as a parallel counter. Then, in case of asynchronous counters, we will connect the clock pulse to the first flip-flop. Then, second flip-flop will be change their state by the previous state output. The clock pulse will repulse from or serially move from one state to the another, one flip-flop to the another flip-flop. So, we will call this asynchronous counters as serial or the ripple counter. Then, synchronous counters having the propagation delay is very less. That means the transmission delay is very less in case of synchronous counters because here the clock pulse is connected directly to all the flip-flops. So, propagation delay is less in synchronous counters. In the asynchronous counters, clock pulse is not connected directly to all the flip-flops. Because of that, propagation delay is high. That is, transmission delay is high in case of asynchronous counters. The main difference between the synchronous counter and the asynchronous counter is synchronous counter change their state simultaneously because clock is connected to all the flip-flops. Asynchronous counters do not change their state simultaneously because clock pulse is not directly connected to all the flip-flops. These synchronous counters can also be called as the parallel counters and asynchronous counters can also be called as the ripple counter or the serial counter. These are the main differences between the synchronous counter and the asynchronous counter. Now, let us move on to the synchronous ripple counter or asynchronous ripple counter or the serial counter. As we all know, the different examples for the asynchronous counter is the ripple counter and the decade counter. Under that, the first one is the asynchronous ripple counter or the serial counter. This asynchronous ripple counter or the serial counter do not change their state simultaneously because clock pulse will be given to the first flip-flop and next flip-flop will change their state with respect to the previous flip-flop output values. The clock pulse or the next clock pulse value will be given to the flip-flop. Then these asynchronous counters are called as the ripple counters because the way in which the clock pulses ripples its way through the flip-flops. Now we'll see how this asynchronous ripple or the serial counter will work. This asynchronous ripple counter or the serial counter will be constructed using the Dk flip-flops. Dk flip-flops. And this asynchronous ripple counter Here 4-bit ripple counter. We will call it as 4-bit ripple counter because it is made up of, or it consists of 4 flip-flop. Flip-flop 1, flip-flop 2, flip-flop 3 and the flip-flop 4. So we will call it as a 4-bit ripple counter or 4-bit serial counter. And this counter will count from 0 to 15. That is, it counts from 0 to 15. That is, it counts the 16 clock pulses. Because 2 raised to the power of 4 is equals to 16. It counts these 16 clock pulses because it consists of 4 flip-flop. Let us observe this circuit. Each of these flip-flop will be having 2 inputs called as J and K because these are the JK flip-flops. These inputs have been joined and connected to the voltage called as VDD, voltage supply. And always this VDD supply, voltage supply, will be in the high state. Here for every flip-flop, the 2 input values have been combined and that will be named as VDD, that is voltage power supply. Because these two have been connected and made it as VDD, always it will be in the high state because as we all know, the JK flip-flops will toggles whenever the J value is equals to 1 and K value is equals to 1. Next, the clock pulse will be given to each of the first flip-flop. And this clock is the negative edge triggered clock because one bubble symbol is here. This bubble symbol indicates that this is a NOT gate. That is, if we fit the clock pulse to the first flip-flop, this first flip-flop will change the state in the negative edge of the clock. Let us observe this clock. This is the rising edge is the positive edge. This is falling edge is called as the negative edge. The flip-flop has to work on the negative edge, that is falling edge. So here we will connect the NOT gate here. Okay, whenever the clock pulse is fed positive edge, that should be converted into the negative edge. So we will be bubbled here. One bubble is inserted here, that is NOT gate is inserted here. This clock we can represent as CLK, or we can also represent it as C. This flip-flop will work on the negative edge or on the falling edge because of this bubble. All these flip-flops will change their states only on the falling edge or on the negative edge of the clock because all flip-flops have been connected to, or the clock have been bubbled. Let us observe, 2 inputs have been joined and that is connected to the voltage power supply, and each of these first flip-flop will be negative edge trigger. This flip-flop will change their state on the negative edge. This second flip-flop will change the state of this flip-flop whenever the output value from the first flip-flop will give it as a input to the second flip-flop. This will act as a clock signal and this will change their state at the negative edge or falling edge. Similarly, the second flip-flop output will be connected to the third flip-flop. Output will be the third flip-flop clock, that too on the negative edge. Next, for the last flip-flop, the F3 or the FF3 third flip-flop output will be connected to the last flip-flop or the fourth flip-flop. Next, here each of these flip-flops is having two output states. One is Q, another one is Q dash. Let us observe each of these flip-flops is having two inputs. Two inputs and two outputs. Outputs are Q and the Q1. These output from the first flip-flop, we will name it as Q1. Output of the second flip-flop, we can call it as Q2. Output of the third flip-flop, we can call it as Q3. Output of the fourth flip-flop, we will name it as Q4. This is the structure of the 4-bit ripple counter. First flip-flop output is connected to the second flip-flop clock input, has a clock input. Second flip-flop output will be connected as a clock input for the third flip-flop. Third flip-flop output will be connected as a clock input for the fourth flip-flop. This is the structure. Now let us start see how it works using the waveform or using the clock signal. For the first time or for the first flip-flop, we will enter the clock. For the next flip-flops, the clock will not be given. Only for the first flip-flop, because it is a asynchronous counter, the clock will be given to only to the first flip-flop. First flip-flop, and this clock will be bubbled here. So the clock will be bubbled here. The Q and the Q dash or the output will change on the negative edge or on the falling edge. Then Q1 will be the output for the flip-flop 1. If we give the first clock pulse, the Q1 will retain in its state until the negative edge comes or the falling edge appears on the clock. If the falling edge or the negative edge appears on the clock, the flip-flop 1 changes its state. So previously the flip-flop will be in the 0th state. Then if it gets the negative edge of the clock, it changes its state from 0 to 1. This is 0 and this is 1 state. And it remains in that state only till it gets next clock pulse negative edge or the falling edge. As soon as it gets, the first flip-flop gets the negative edge or the falling edge of the second clock, it changes its states from 1 to 0. This is 1 and this is 0. Next, it retains its state till it gets the next negative edge or the falling edge. The next negative edge or the falling edge appears here, then it changes its state from 0 to 1. 0 to 1. 0 ಇಂದ 1ಕ್ಕೆ reach ಆಗಿದೆ. Next, it retains its state in this state only. Next, it reaches or this flip-flop 1 reaches or gets the next negative edge. This is the next negative edge of the falling edge. If it gets the next negative edge of the falling edge, the flip-flop 1 will change its states from 1 to 0. That means Q1 value will changes from 1 to 0. And the Q1 will be, or the state of the flip-flop will be in the same position, 0th position, till it gets the one more clock negative edge. If it gets the negative edge, it will be in the same state, and if it gets the negative edge, the flip-flop state will be changed from 0 to 1. This pattern continues for all the negative edges. For the negative edges or for the falling edges, the flip-flop state will be changed and it reaches to the 15 clock pulses. For the first time, all the flip-flop output values, that is Q1, Q2, Q3 and the Q4 will be in the 0th state, that is 0. For the first clock period will be entered to the first flip-flop. The Q1 value will changes. Q1 value will be changed for every negative edge of the clock. Negative edge of the clock ಎಲ್ಲೆಲ್ಲಿ ಬಂದಿದೆಯೋ ಅಲ್ಲಿ ಫಸ್ಟ್ ಫ್ಲಿಪ್ ಫ್ಲಾಪ್ ಸ್ಟೇಟ್ ಚೇಂಜ್ ಮಾಡ್ತಾ ಇದೆ. See here, ಇಲ್ಲಿ 0 ಇದ್ದಿದ್ದು 1 ಆಯಿತು. ಇನ್ ದ ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಕ್ ಪಲ್ಸ್ ಇಲ್ಲಿ 1 ಇದ್ದಿದ್ದು 0 ಆಯಿತು. ಇನ್ ದ ಸೆಕೆಂಡ್ ಕ್ಲಾಕ್ ಪಲ್ಸ್ ಇನ್ ದ ನೆಗೆಟಿವ್ ಎಡ್ಜ್ 0 ಇದ್ದಿದ್ದು 1 ಆಯಿತು. ಇನ್ ದ ಥರ್ಡ್ ಕ್ಲಾಕ್ ಪಲ್ಸ್ 1 ಇದ್ದಿದ್ದು 0 ಆಯಿತು. Similarly, observe here, for all the negative edge of the clock or the falling edge of the clock, Q1 values will change. Q1 values will change. Now, this Q1 value or this Q1 clock will act as a input to the second flip-flop, because for only the first flip-flop we will enter the day clock. For the next flip-flops we won't enter the clock pulse. The output of the first flip-flop will act as a input clock to the next flip-flops. So this clock will be the clock input for the first flip-flop. Then according to this clock, the Q1 value will change on the negative edge or on the falling edge. Next, this Q1 output will act as a input for the second flip-flop to change the state of this flip-flop and to get the value called as Q2. Q2 value ಬೇಕು ಅಂದ್ರೆ ನಮಗೆ ಈ flip-flop state change ಆಗಬೇಕು. ಈ flip-flop state change ಆಗಬೇಕು ಅಂತಂದ್ರೆ ನಮಗೆ ಫಸ್ಟ್ ಫ್ಲಿಪ್-ಫ್ಲಾಪ್ದು ಔಟ್ಪುಟ್ ಬೇಕು. ಫಸ್ಟ್ ಫ್ಲಿಪ್-ಫ್ಲಾಪ್ ಔಟ್ಪುಟ್ ಯಾವುದು ಕನೆಕ್ಟ್ ಮಾಡಿದೀವಿ? ಸೆಕೆಂಡ್ ಫ್ಲಿಪ್-ಫ್ಲಾಪ್ಗೆ ಕ್ಲಾಕ್ಗೆ ಕನೆಕ್ಟ್ ಮಾಡಿದೀವಿ. ಸೆಕೆಂಡ್ ಫ್ಲಿಪ್-ಫ್ಲಾಪ್ ಕ್ಲಾಕ್ ದಟ್ ಇಟ್ ಈಸ್ ಬಬಲ್ಡ್. That means this will change the state on the falling edge. Now, according to this, ಈ Q2 ವ್ಯಾಲ್ಯೂ ಬೇಕು ಅಂತಂದ್ರೆ Q2 ವ್ಯಾಲ್ಯೂಗೆ ನಾವು ಬರಿಬೇಕು ಅಂತಂದ್ರೆ Q2 ವ್ಯಾಲ್ಯೂ ಬೇಕು ಅಂತಂದ್ರೆ we need the value of Q1. That means here this Q1 output will act as a clock input for the second flip-flop. This Q2 we can get based on this Q1 values. As we all know, here the flip-flops will work on the negative edge. Q2, that is second flip-flop, will change its states until it gets the negative edge from the previous flip-flop output value. Let us observe here. This is a clock. This will act as a clock for the second flip-flop. This Q2 will retain in its state until it gets the negative edge or the falling edge from the Q1 output. It will be in the 0 state. It will be retain its state in the 0th state until the negative edge comes. If the negative edge appears, next it changes the states from 0 to 1. Next, it retains its state in the 1 state only until it gets the next negative edge or the falling edge. If it gets the negative edge or the falling edge, it changes its state from 0 to 1. 1 to 0. It changes its states from 1 to 0. It retains its state in the 0th state until it gets the negative falling edge. If it gets the negative falling edge from the previous flip-flop output, it changes its state from 0 to 1. Next, it retains its state until it gets the negative edge. ಇಲ್ಲಿ ನೆಗೆಟಿವ್ ಎಡ್ಜ್ ಬಂತು. ಇಲ್ಲಿ ನೆಗೆಟಿವ್ ಎಡ್ಜ್ ಬಂದಿದ ತಕ್ಷಣ ಇಲ್ಲಿ 1 ಇರೋದು 0 ಆಯಿತು. In this pattern, the Q2 values will change and it reaches to the 15th stage. Next, the flip-flop 3 will change its states whenever the clock input from the previous flip-flop called as the flip-flop 2 will be fed as a clock input to the flip-flop 3. Then Q2 will act as Q2 output will act as a clock input for the flip-flop 3. Then this flip-flop 3 will change their state and will get the values of Q3. Only the Q2 value will fed it to the flip-flop 3. Let us observe with respect to this. To get the value of Q3, this Q2 will act as a Q3 for getting the output values for Q3. Initially, the Q3 will be in 0th state. This Q3 changes its state from 0 to 1 till it retains its state in that 0th state. It will wait that state. If it gets the falling edge or the negative edge, it changes its states from 0 to 1. 0 ಇಂದ 1ಕ್ಕೆ ಯಾವಾಗ ಚೇಂಜ್ ಆಗುತ್ತೆ ಅಂತಂದ್ರೆ Q2ದು ನೆಗೆಟಿವ್ ಎಡ್ಜ್ ಅಥವಾ ಫಾಲಿಂಗ್ ಎಡ್ಜ್ ಬಂದಾಗ. Whenever it gets the negative edge or falling edge, it changes its states from 0 to 1. It retains its state in this high state only till it gets the negative edge in the clock, because this acts as a clock input for this flip-flop output. If it gets the negative edge, it changes its state from 1 to 0 and it retains its state in the 0th state and it will be changed or moved back to the 1 state in the negative edge. Okay, in the 15th stage also, it reaches to the last falling edge at the negative edge, then it changes its states from 1 to 0. This is the output of the Q3 or the flip-flop 3. Finally, the last flip-flop is flip-flop 4. This flip-flop 4 will changes its state whenever the output value from the flip-flop 3, that is Q3, will be fed as a input to the flip-flop 4. ಈ flip-flop 4 ಯಾವಾಗ ಸ್ಟೇಟ್ ಚೇಂಜ್ ಮಾಡುತ್ತೆ? whenever the ಔಟ್ಪುಟ್ ವ್ಯಾಲ್ಯೂ Q3 ನಾವು ಇದಕ್ಕೆ ಕೊಟ್ಟಾಗ ನೆಗೆಟಿವ್ ಎಡ್ಜ್ ಯಾವಾಗ ಬರುತ್ತೋ ಆಗ ಫ್ಲಿಪ್ ಫ್ಲಾಪ್ 4 ಸ್ಟೇಟಸ್ ಚೇಂಜ್ ಆಗಿ Q4 ಔಟ್ಪುಟ್ ವ್ಯಾಲ್ಯೂ ಬರುತ್ತೆ. To get the Q4 values, the clock input we require, this Q3 will be act as a clock input for this flip-flop to get the values of Q4. Now, let us observe here. Q4, initially it will be in the 0th state. This Q4 will change its states if it gets the negative edge. It retains its state called as 0 till it gets the negative edge. Once the negative edge sikkide andaga, it changes its states from 0 to 1. 0 ಇಂದ 1ಕ್ಕೆ change ಆಗುತ್ತೆ and it retains its state ಒಂದೇ ಸ್ಟೇಟ್ ಅಲ್ಲಿ ಇರುತ್ತೆ. It is in state 1 till it gets another negative edge. If it gets the another negative edge, it changes its states from 1 to 0. In this fashion, the 4-bit asynchronous ripple counter or the serial counter will work. For the first flip-flop, clock pulse will be given. It will be work on the negative edge. The first flip-flop output will be given as input to the second flip-flop. The second flip-flop changes its state based on the Q1 values. Then third flip-flop changes its state based on the flip-flop 2 output called as Q2 values. Flip-flop 4 will changes its state based on the output of flip-flop 3 because it is given as a clock input. Let us observe this waveform here. Here 15 clock pulses are there. Finally, if it reaches the 4th stage or the Q4, this waveform or the clock pulses, this frequency will be divided into all. So, these type of counters can be used for frequency dividing purposes. And let us observe these clock signals. These clock signals are rippling or going or transmitting serially. So we can name this synchronous or the asynchronous counter as the ripple counter or the serial counter anta kariತೀವಿ. Now let us write the truth table by considering this waveform. The main purpose of the counter is, as we all know, it is used for counting purposes. Counting purposes means for every clock input pulse, it should be incremented by 1. It should be incremented by 1. That means if we pass 0 to 15 clock pulses, for every clock pulse it has to be incremented by 1. Now it should pass to or count from 0 to 15 states. That means 0 ಇಂದ 15 ವರೆಗೂ ಅದು count ಆಗಬೇಕು. This is in the initially the state of the flip-flop, the values for Q1, Q2, Q3 and the Q4. Q1 is the output of the first flip-flop, Q2 is the output of the second flip-flop, Q3 is the output of the third flip-flop, Q4 is the output of the fourth flip-flop. Initially, observe here, all the output values of the flip-flops is 0. This is 0, 0, 0, 0, 0. Next, ಅದಕ್ಕೆ ನಾವು ಇಲ್ಲಿ ಏನು ಹಾಕಿದೀವಿ 0, 0, 0, 0. This is the 0th stage. If the first clock pulse is fed, for the first clock pulse on the negative edge ಬಂದಾಗ, let us observe what is the state of the flip-flop. Q1 value will be 1. Q1 value ಏನಿದೆ ಇಲ್ಲಿ 1 ಇದೆ. Q2 value 0 ಇದೆ. Q3 value 0 ಇದೆ. Q4 value will be 0. Q4 value will be 0. Next, for the third clock pulse, for the third stage, let us observe here, third stage alli, what are the Q1 value for the third clock pulse, for the first negative edge. For the first negative edge bandaga, values will be Q1 value, Q1 it is in the value of 0. 0 ide. Next, Q2 value 0 ide. Q3 value 0 ide. Q3 value 0 ide. Q4 value 0 ide. Except for the first, Q1 will be in 1. Idu 1 ide. Next, Q2 value will be 0. Q3 value will be 0. Q4 value will be 0. Now adike 0, 0, 0, 1. BCD conversion or the binary decimal conversion of 0, 0, 0, 1 is 1. For the next stage, for the next clock, for negative clock pulse, for the next clock pulse, Q1 will be in the 0, Q2 will be in 1, Q3 will be in 0th state, Q4 will be in 0th state. See here, except for Q2, all will be in the 0th state. So, for the next clock pulse, for the second stage, it is 0, 1, 0, 1. For the third clock pulse, Q1 will be in 1, Q2 will be in 1, Q3 will be in 0th state, Q4 will be in 0th state. That is, for the third state, Q1 will be 1, Q2 will be 1, Q3 will be 0, Q4 will be 0. For the fourth state, Q1 will be in the 0th state, then Q2 will be in the 0th state, Q3 will be in the 1 state, Q4 will be in the 0th state. That means 0, 1, 0, 0, 1 and 0. BCD conversion of 0, 1, 0, 0 is 4. Let us observe here, the output values of the counter will be incremented by 1 for every clock pulse. Here, the BCD conversion of this 0th state is 0. This is BCD conversion of 0, 0, 0, 1 is 1. Decimal conversion of 0, 0, 1, 0 is 1. It is, let us, next decimal conversion of 0, 1, 0, 0 is 4. It is incrementing by 1. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let us observe here 15th negative edge of the clock. All the output values will be in high state. Q1 will be in high, Q3 will be in high, Q4 will be in high, Q3 will be in high and Q4 will be in high. Let us observe values here also. All the output values will be high. That means it reaches to the last stage. It counts from 0th stage and its last stage is 15 because 4 flip-flops are there. Last stage is 1111. That is decimal conversion is 15. It reaches to the last stage. Last stage ge reach agid takshana, you should wrap back to the initial stage or it will wrap back to the 0th state. This is how the counters will increment for every clock pulse. Every clock pulse and data we will fed to the flip-flop in the digital form. It will be counted one by one for every clock pulse. That too in the asynchronous counter, the clock pulse will be the negative edge. On the negative edge, it will count and it will count from 0 to 50. This is about the asynchronous ripple or the serial counter. Next we'll move on to the next type of counter called as the decade counter or the mod 10 counter. In the decade counter or in the mod 10 counter, it will count from 0 to 10. The asynchronous decade counter can be constructed with a little bit change in the asynchronous counter. Let us observe the flip-flops here. These flip-flops will be of JK flip-flops and inputs will be joined and this will be made as a logic one, that is always it will be in the high state. For all the JK inputs, it will be joined and it will be connected to 1 as in the asynchronous ripple counter. Then output of the first flip-flop will be given as the input to the next flip-flop. Output of the second flip-flop will be given as the input to the third flip-flop. Then output of the third flip-flop will be given as input to the fourth flip-flop. Then the counting here should stop at the 10 because this is the 4-bit counter. It counts from 0 to 15. This we need to modify and we should made it to count up to 10. 10 ವರ್ಗೂ ಅಷ್ಟೇ ಕೌಂಟ್ ಆಗಬೇಕು. ನಮಗೆ 15 ವರ್ಗೂ ಕೌಂಟ್ ಆಗಬಾರದು. For that purpose, we will alter this circuit to stop the counting at 10. ಈ ಕೌಂಟಿಂಗ್ 10 ವರ್ಗೂ ಕೌಂಟ್ ಮಾಡಿ 10 ಇಂದ ಮತ್ತೆ 10 ಗೆ ಬಂದಿದೆ ಅಂದ್ರೆ ಮತ್ತೆ 0 ಇಂದ ಸ್ಟಾರ್ಟ್ ಆಗಬೇಕು ಕೌಂಟಿಂಗ್. For that purpose, for the last flip-flop, output value will be connected to the AND gate. The last output value will be connected and the first output flip-flop output value called as the QA will be connected to the AND gate. because it should stop counting at the 10. ಅದಕ್ಕೋಸ್ಕರ there is a change and output value QD ಮತ್ತೆ output value QA is connected to the AND gate and also clock input is connected to the AND gate. If it reaches the 10, it will be moved back to the 0th state. With these changes, we can construct the asynchronous decade counter to count from 0 to 9. If it is reaches the 9th state, that is 1001 state, it will be moved back to the 0th state. Let us observe here. It is displaying the decimal value 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9. Then counter resets its output back to the 0. It stops at this stage because of this AND gate. This is called as the decade counter or the asynchronous decade counter. Till now, we have seen the concept of asynchronous ripple counter and the asynchronous decade counter. The difference between the asynchronous ripple counter and the decade counter, in the asynchronous ripple counter, the ripple counter, the serial counter counts from 0 to 15. The decade counter counts from 0 to 10. Till now, we have seen the concept of counter and its types and the first type of counter called as the asynchronous counter. Then we'll move on to the multiple type of questions that will appear in the activity or the quiz. Now let us start with the questions. The first question is the counter can also be defined as a sequential circuit consist of set of flip-flops used to count the sequence of dash pulses presented to in the digital form. Here the question is what type of pulses it is counting, and they will specify the answers as multiple choice like A is input, B is output. Let us recall the counter definition. Counter is used to count the input clock pulses that we will present it in the digital form. So the answer for this question is input. The next question is counters can act as dash to keep track of the time. As I told you in the benefits, please recall this topic. The counters is used for the counting purpose. So it can be used as the simple clock for keep track of the time. So the answer is clock. The next type question is how many types of counters are there? Let us think on recall. There are two types of counters are there. One is asynchronous counter, another one is synchronous counter. Now the answer is 2. Then we should select the answer as B here. Next, fourth question is 4-bit ripple counter is an example of which type of counter? Recall the topic. Ripple counter or the serial counters are the examples for the asynchronous counters. So, ripple counters are the asynchronous counters. So, the answer is A. Next question is in which counter all the flip-flops do not change their state simultaneously. Do not change their state simultaneously. In the asynchronous counter, all the flip-flops do not change their state simultaneously. So the answer is A. So the answer is A. These are the different types of questions that may appear in the activity or in the quiz. Till now, we have seen the concepts of the counters and the benefits and the comparison of the counter and the asynchronous ripple counter and the decade counter. Thank you all.